Okay, so we're going to start chapter 10. This is concerning with categorical data. Hopefully this video will work out all right. I might scoot it slightly closer. Cool. Okay, so in chapter 10, we're dealing with categorical data. So what categorical data means is that the data we have isn't like numeric necessarily, it's just in categories. So maybe the category, the response variable might be yes or no, or maybe we want to rank the responses and put them in slots, like slot 0, slot 1, slot 2, in order to record that. And we want both the independent, the input variable, and the dependent, the output variable, to be categorical. And I'll show you an example which will hopefully clarify that. Okay, so for our inputs, our data, we're going to consider populations that we've divided into 2 or more subpopulations. These will be categories, okay, for our population, our input data. And our response variable will also be categorical. And in general, what we're going to be trying to do is we're going to try and answer questions of the form, is the response variable output independent of the subpopulation? So no matter where the data row was from which subpopulation, is it equally likely to have a response variable of yes versus no? Okay. And the nice thing throughout this entire chapter, we're only going to be dealing with one test statistic that we're going to use to answer questions, and that's the chi-square test statistic. And this, like this fancy x squared, that's the chi-square symbol. Okay, so by the magic of wheels, we're going to wander over to the next screen, and hopefully you'll be able to get it all in there. Might zoom in at first and then spin us. You can just fast forward this, obviously. Oh, I'm going the wrong way. Okay. Your motion's sick. It's okay. You can puke and come back. All right. That's looking pretty good. Okay. So again, I'd sort of recommend like pausing the video, copying this table down. You're going to need this table for later screens this video. Okay. So, pause it. Off you go. All right, so here's a typical question. We've got 2 categorical variables. The input has I subpopulations, and the output, the response variable, has J groupings, okay? And in our case, we're going to ask, are the 2 categorical variables independent of each other, okay? I'll wander over here for now. All right. So in this example, we've gathered a bunch of data and we've asked a bunch of people, are you in favor or do you oppose the death penalty? And we've grouped these people by their education levels. So we've got people who did not get a high school diploma. They left high school before they graduated. People who highest educational level is a high school degree. People who went to junior college. People who achieved a bachelor's degree. People who achieved a graduate degree. And in total, we asked 1,307 people, okay? So the left high school, 117 favored it and 72 opposed it, and there were 189 high school people that we asked, or left high school people that we asked. 511 and 200 for the high school degree people, of a total of 711 high school degree people. 71 junior college graduates favored the death penalty, 16 opposed it. 135 people with a bachelor's degree favored it, 71 opposed it. 64 people with a graduate degree favored it, 50 people opposed it. So in black is our raw data, okay? I've then summed up the rows and I've summed up the columns, and if you add 898 and 409, you'll get 1307 as you will with this one. Okay, this next column is what percentage of this category favored the death penalty. I could have done which percentage opposed, didn't matter, so I just stuck with favor. So 117 of the 189 people who didn't complete high school favored it. So that was 61.9%. Similar calculations all the way on down. And in total, 898 of the 1,307 people favored the death penalty. So of all the people we asked, it was about 69% who favored the death penalty, all right? Now, if education level and death penalty opinion were independent of each other, I would expect each of these educational categories to have about 68.7% favoring the death penalty. Now we don't. And so let's just see what we should have expected, and that'll be in the red. So if they were independent, I would have expected 68.7% of each of these subpopulations to favor the death penalty. So 68.7% of the 189 people who didn't finish college or high school, would have been about 130. 68.7% of the 711 people whose highest level of education was a high school diploma would have been 488.5 who favored the death penalty, and so on and so forth. And I could do the exact same thing with the expected number who should have opposed the death penalty. So it's 1 minus 0.687 times all the non-high school degree people, 1 minus 0.687 times all the high school degree people, and so on and so forth. So I have the expected favoring and the expected opposing. Okay. All right. So black, original data. Green is just computations in the original data. And then red is what we should have expected were favoring death penalty and education completely independent of each other. All right, so you need to have this down before I slide over. So make sure you copy that down. And then we'll slide our way on over. Okay. Actually, I want space over here. All right. So then, again, pause, copy this down, and then I'll channel on. So that is, is favoring, the question we're trying to answer is favoring or opposing the death penalty independent of one's education level, right? That's the question. If so, each education level should exhibit approximately 68.7% favoring level. And the question we want to ask is, how can we measure how close to or how far from this ideal or this independent assumption our data is? And that's where the chi-square statistic is going to come in. So with the chi-square statistic, we're going to sum over all 5 times 2 cells that we began with, the black cells. So we had 2 black cells for people who didn't complete high school, 1 for favoring, 1 for opposing. We had 2 black cells for people who got a high school diploma, 1 for favoring, 1 for opposing. And we had 5 educational levels. So that's the 10 cells that we're talking about here, okay? For each of those cells, we're going to take what we observed, the actual responses we get, minus the expected, and that was that red column, the expected number who should have favored the death penalty if these 2 things are independent, education and death penalty are independent. So we're going to have observed minus expected. We're going to square it to kill off any minus signs so that differences don't cancel each other out when I add them together, divided by the expected number for that cell. And I'm going to sum those all together, and this will get abbreviated by O minus E quantity squared over E. O for observed, E for expected. Okay, so first view. Here was people who didn't get a high school degree. 117 favored the death penalty. But the expected number favoring it, we calculated at 129.9. Here's the number of people who did not get a high school degree that opposed the death penalty, 72. But the expected number who should have opposed the death penalty was 59.1. Okay, so I'm going to do that computation for each cell. And here's the graduate school people. So 64 people with a graduate degree favored the death penalty. We would have expected 78.3. And 50 people with a graduate degree opposed the death penalty. We would have expected 35.7. So I crank out that sum and I get the number 23.45, which I'll denote as C, okay? And the question is, how do we interpret this test statistic? What is it actually telling us, right? Is it telling us that it's highly unlikely that this C value could have been created if the education level and the death penalty opinion were independent of each other? Or is it saying, well, yeah, this could easily have occurred by chance, right? Okay, so how do we interpret it? And in this chapter, we're going to look at 3 ways to figure out how to interpret that 23.45 value. First way is going to be permutation testing, which I'll do on the next board over in this video. Then we're going to look at an actual more mathematical way, which is the chi-square distribution. That'll be 10.3.1 and 10.3.2. And then we'll look at some exact calculations, which pre-cheap computing would have been highly in vogue, okay? And that will be the Fisher's exact test with some conditioning in 10.3.3 and 10.3.4, okay? All right, so let's roll on over to the last board for this video at least. And we're going to look at permutation test. There we go. Cool. Okay. All right. So hopefully you can zoom in and read this. Maybe at the end of the video, I'll scroll back through, do close-ups. I wonder if I can do that. Okay, so here's how we take that value of 23.45 and interpret it via permutation test, which we're somewhat familiar with. So first off, for the permutation test, let's imagine our raw data as, I think we had 1,307 people altogether. So let's imagine we had 1,307 rows of data. All of my non-high school completers are the first lumping of rows. All of my people with a high school diploma are my second lumping of rows. All the people who got a junior college degree are my third lumping of rows, et cetera, et cetera, et cetera. So I'll have the name in the first column. And the second column is going to be favor or oppose. There's going to be an F or an O or maybe a 0 and a 1, something like that in my second column. From that column, I created the contingency table on that second board that we saw, okay? But imagine each row is a certain person and the rows are grouped by their education level. And there's one column that says opposed or favors, okay? And that's the one column we're going to be permuting in a permutation test. Okay, so steps. If the two categories are independent, education level, opposing, favoring, death penalty, if those two things are independent, we should be able to permute the entries of one column, the favor opposed column, while keeping the other column fixed. Like we're going to keep this person in the educational level we found, but maybe just permute their opinion of the death penalty. Okay. And then any permutation should be equally likely. So for each permutation, we're going to then create the contingency table that was on that second screen and compute the C value, the chi-square test statistic for that revised data. We're going to repeat that 10 to the 4th or 10 to the 5th times, keeping track of our different chi-square test statistics and create our permutation distribution of that chi-square test statistic. And then we'll compute the p-value for our observed chi-square test statistic for 23.45. Okay. Now, for example, if I permuted the favor opposed column one time, this could be the contingency table that was created. So in this case, 127 people who didn't complete high school favored the death penalty, and the rest of them, 189 minus 127, opposed it. Okay. Because remember, I'm not changing the educational level. So the total number of non-high school diploma people should remain the same. So I'm just permuting the oppose or favor column, right? And keep in mind, since I'm permuting the oppose or favor column, the total number of people who favor and oppose are unchanged. So I've just permuted those values, okay? So there would be one contingency table from permuting the data. Now, via R, which I'll show you in a hot second here, for the 23.45, we got a p-value of 0.00012. So it's incredibly unlikely to get a C value, 23.45 or higher by chance, okay? So this is highly unusual, which indicates that there is an association between education level and favoring or opposing the death penalty. So we can say that there's statistically significant evidence that shows that these two categories are not independent of each other, okay? All right, so I'm just gonna, before I pop up the C code, I'm just gonna hopefully zoom in on any words that you're having trouble with. And if we start back at the beginning, certainly pause wherever you need to. Green doesn't seem to show up too well. The red's pretty good. And then the last column. Okay. So now I'm gonna flip over to the R code and just run through it. Okay. Right. So I've again got my resampling data popped up. There's this chi-square function, which I don't exactly know what it is, but I'm going to run it, and it just ran a whole chunk and didn't really output anything. I'm going to declare some new data. There's my education level, so I'm going to grab that education column. I'm going to grab the death penalty column, which says whether you oppose or favor. There's some alternate code there if you wish to take the hashtags off of them. I'm going to create a table, and this is the table we had on the board earlier. And I'm then setting my different levels of education. So I just created categorical variable for education. And I told R that I'm only going to consider groupings of left high school, junior college, bachelor's, or graduate. So it just grouped all the data into those 5 categories. Okay. I'm then going to run my chi-square code. That's going to be the sum of my observed minus expected squared over expected. I'm going to run that on that contingency table, education and death penalty. Okay. And it tells me the chi-square test for independence is 23.5, which we got. What we got? 0.45 base, they rounded up. And then for some reason, I wanted to see that number with more decimals, so they agreed with our 23.45. Okay, I'm going to index, getting rid of any entries that didn't have something for education or death penalty. And then, so the index counted up or indexed all the rows that we didn't have complete information for. So then I'm going to stick with the opposite of that, the negative index. Those are the rows we do have complete information for. That's negative index, and death penalty will be the negative index as well. Right, now here we go with our permutation test. I'm going to do this 2 to the 4 plus 1 times. I create a vector to store my different C values in. And then I'm going to start my loop here, and I'm going to permute the death penalty, that means. Okay. Does hopefully. There we go. Okay. This code looks a little different than the output, so I might have screwed something up, but let's see. Create my histogram. Yes, I did. Let me go back to that loop and rerun it. I think by highlighting it messed something up. So I'm going to do index that. It's thinking, and still thinking. It's taking a long time to think. Well, we got quite a few rows of data, I guess, so permutation is going to take a while. And it is early. So there it goes. I create my histogram. There it is. I'm going to throw in my observed line, and it's way over there on my right. And now I'm going to calculate my p-value. 2 times, it's the result being greater than the observed chi-square value plus 1 over n plus 1. So it's that original chapter 2, chapter 3 permutation test. And I got a p-value 3 times e to the negative times 10 to the negative fourth. Just slightly different than the one I put up on the board, but it's permutation, so differences happen. And then we can figure out p values using our raw data, and there the p-value is 2 times 10 to the negative fourth. And I can also do it via contingency tables. And there I get a p-value of 1 times 10 to the negative fourth. Okay, so for us, it's not going to really matter which of these techniques we use for permutation tests. We're just going to crank one out. Okay. All right, so that's it for the first video.